Okay, that's the electronic flycatcher here. It's old, and yeah, I want to have the module which generates about 600 volts out of here. And but I see, yeah, the grip here is secured by several screws, and at least one screw here is a special screw, and I don't have a bit for that. But yeah, first of all, as it is old, I haven't used it several years, so I first want to make sure that this thing works. So one cell and the second cell, and then, oh yeah, it's the hissing sound here, or beeping sound I want to hear. So let's see if it's really generating high voltage. Just let me grab some aluminium foil here. Okay, there it is, and I have a grip here which is good isolated, because I don't want to get shocked here. So let's see. I don't see no sparks. Why is that? Let's try again. Ah yeah, okay. So there is high voltage there.
Yes.
That's good. So it's working. So it's worth disassembling. So let's first pull out the batteries here, because I really don't want to get shocked. So let's see. I need to get the screws loose here. Okay, that's the first one. Ta-da! And yeah, the other ones are too deep for my screwing bit, so I have to look out for another screwdriver. Okay, there it is. I hope it fits. It's good enough. Oh, no. It's yes, too thick. I have to look for another one. Okay, this one is thinner here. Let's see. Yeah, that looks good. Apart. Okay, that screw is loose here, and that as well. But of course, that damn special screw is not. But I don't care. I just break it off then. So then I can use my grip here and just can turn it out that way. But yeah, actually I don't need to undo it, because yeah, what I want to get my hands on is that module here. That module generates from 3 volt nominally DC a voltage of round about 600 volts. I have to measure that later on, but no. Anyways, I have to get the screw off here, because otherwise I'm not able to see how it is exactly attached there. So I think that should be enough. Oh yeah, thank God. So come on. Yes, yeah, that's good. Okay, 2 wires, or 3 wires actually. Let's see. I see the module has one screw there. Let's see how they wired that. Okay, so let's see that one wire goes to that mesh at the top and the other wire goes to the mesh on the bottom, and the third wire goes to that smaller grid there in the middle. So I think maybe, yeah, that grid in the middle is plus, and both wider grids here on the top and the bottom are minus, or vice versa. Doesn't really matter. Okay, I want to detach that. I need a wire cutter. Okay, I got a wire cutter here. So let's just cut this off. 1, 2, and 3. So okay, that part is apart. So I just have the grip here with the module, and I want to keep it that way because, yeah, so I have the battery compartment here, and yeah, the module is encapsulated because, yeah, no one wants to actually accidentally come in contact with it. So in the module itself, we see a transformator here, and there's a diode, another diode, a resistor, 2 other resistors, an LED, and a transistor. And the transistor is what is it? T128 or something? Yeah, I think it's a Chinese type, whatever. But I think that's a standard oscillator. And yeah, the transistor switches the primary circuit of the transformator on and off, and on the secondary windings there is the higher voltage, and this is then rectified by the 2 diodes and filtered by that capacitor here, and it's a 474J, but it's a pretty small capacitor because yeah, it is intentional that there's not much energy stored in it, because if there's too much energy stored in that, yeah, the shock here would be lethal, and yeah, we don't want that. So there's another resistor, and that's the bleeding resistor to, yeah, bleed the charge off so that it is, yeah, at 0 volts in a short time. So yeah, now I have to measure the voltage, the output voltage somehow. Let's see. Okay, yeah, I have 2.145 megohm resistors here, and I want to use these to, yeah, divide down the around about 600 volts, because, yeah, maybe it's not 600, maybe it's 800 or 1000 or 1200 or something, and my multimeter just accepts the maximum of 1000 volts, and I don't want to screw it. So I, make a high voltage divider, and one resistor usually, is capable to withstand 200 volts. So I have to use at least 3 ones. Because, yeah, 2, 4, 6, then we have 600, but maybe it's better to use 4, because, yeah, then we have 800 watts, or even 5, because then we have 1000 watts. I have to see how much patient I am with soldering it. And there's also the power rating, and I calculated with 600 volts, and if I just connect one resistor to 600 volts, I have a power loss or power on the resistor of around about 170 milliwatts. That's okay, because the resistors are rated for 200 milliwatts. And if I use, for example, 4 resistors, it is just 42 milliwatts per resistor, and that should be fine. And the resistors shouldn't sweat too much there, and at least get lukewarm. I'm going to use this perf board here because it's just temporary, and of course it is a good idea for better isolation to put the resistors on a longer distance here, so not one next to the other or packed in parallel, because then the high voltage could jump over from one resistor to the other. So I don't want to happen that, and that's why I intend to use the whole length here. But it has not to be pretty broad. So let's see. I think that's fine here. Okay, and then I can just break it over that edge here. Okay, there it is. Okay, just cut out the resistors here, and I think I just use 4 resistors. That should be sufficient, and then it's easier to calculate, because I have to just multiply the measured voltage by 4. So let's see, I want to do it tight here. That looks good. Let's see, how can I do it? I want to spread these as much as possible here. Maybe I can do a zigzag pattern here. Let's see how that works. So 1, 2, 3, 4. Okay, I can step into the perf board, because on the edge I want to have a contact where I can put a grip contact on it. And let's see, bend it over here. So okay, that looks good. I'm satisfied. So then I can do it the same way with the other 3. Okay, there we have it. Let's see. Yeah, that looks good. Oh, it's crooked here. So again. One there. Oh no, it's the other one. So like that. So we have 1, 2, 3, 4 holes in between, like here. So that's good. And that way I have enough space here to add more resistors if necessary. But I'm lazy here. I do it with just 4 resistors. I mean, yeah, my multimeter can withstand 1000 watts, so that means it gets 1/4 of the voltage at the whole distance here. I think it should be fine. Maybe I don't use my best multimeter. But yet now I have to solder these. So there's just one interconnection missing. That's it. Maybe I just leave it. Then I have measurement points. Just bend them to the side. Yeah, I think that's good. Yeah, but now I have to somehow connect it to the high voltage generator. Oh, come on. There we go. That's really a flimsy cable here. But yeah, anyways, it is what it is, and I have to use what it is. I just want to solder the end because otherwise it will fall apart, I think. At least when I connect it, 2, 3 or more times. Oh yeah, that looks better now. See? Okay. And yeah, I will twist these 2 wires here because they have the same potential anyways. Hopefully I can solder these. Let's see. Okay, doesn't matter which way I connect it. At least I think it doesn't matter. And yes. Yep. Takes solder here. That's good. So let's say this is the ground point here then. And is the high voltage point. Yeah. Okay, everything is connected now. Now I get rid of that aluminum plate here. Because I need a little bit of isolation here. And yeah, then I want to measure the voltage. Yeah, and of course the voltage will appear across these series of resistors, and I want to measure the voltage, yeah, which is at the lowest resistor here, from there to there. And for this, I want to use this measurement device. It's analog, as you see, and has a rating of 1000 volts max here. Just that you have the reflection here from the light, but I think this way it should work. Then I just have to connect ground lead to the ground and the positive lead to the terminal of this resistor here. Okay, and when I now insert the battery cells, 1 and 2, just lift it up here that it's in the air, then we have better isolation here, because yeah, 600 volts is the thing. And yeah, if we have 600 volts across these resistors here, we should see 150 volts across this resistor here. So let's see if the needle jumps when I now push the button. Yeah, yeah, that looks good. And we have 220, 240, 230 volts. Okay, 230 volts. That's more than 150 watts. So obviously there's more than 600 watts here. And if I calculate that, 230 times 4, that's 920 watts max. So that's a lot of voltage, but it's below 1000 watts. That's good. And let's repeat that, see if it's repeatable. Yeah, seems to be steady. Maybe I can just go one range lower. Then we have 250 max, then it's this range here. Okay, that's more precise. That's 200 volts. And yeah, if this is true, it's 800 volts across all resistors here, which comes from the high voltage generator. That's a difference now. Let's see if it's repeatable. Yeah, 200 volts. So yeah, obviously it's 800 watts total. So yeah, now I have to add a series resistor here because yeah, I need that to limit the current when I apply the 800 volts to the device under test. I mean, then the current is already limited by resistors here on the PCB, but for safety I want to limit the measurement current to about 1 milliamp. So yeah, I have to solder 800K or something like that, like this. Of course, yeah, divided by several resistors, because yeah, every resistor has actually 250 volt rating. So yeah, preferably I do it with 3 or 4 resistors. You can just disconnect that here. And yeah, I have 200K resistors here. And yeah, I want to use these as a series resistor. And I use 4 of them. Then I have 1 meg actually, roundabout. I just have to bend them again. Oh, they are longer, have a longer body here. And that's probably because they have a higher voltage rating. The third one and the fourth one. Yeah, and again I want to put it in a zigzag pattern. Let's see. Okay, so yeah, that looks good. It's space saving here. And yeah, again, then I can put a wire from there to there, and that's the starting point and that's the end point, and I interconnect the closer pins here, and then this is my series resistor. Just have to solder it, of course. And there we have it. Yeah, now the positive terminal is routed to the starting point of the series resistor and then crisscrossing over to here. And that's my output actually. That's the output terminal then. I just want to shorten these pins here because they're prone to accidentally make a short circuit here. And that's not good. Okay, then that is finished. So the voltage divider divides the voltage to a lower safe level, and the combined series resistor limits the current to a safe level. So I can now make a first test, and for this I want to use this analog multimeter. I've set it to 1000 volt range, and then I have to connect it ground to ground. That's good. And basically I want to measure the voltage above one resistor here, not to overload my multimeter, and that's then here. See, is that true? Yeah, that's true. Okay. So let me arrange that you can see what's going on. So multimeters out of the reflection here, that's good. And yeah, batteries are already inserted, and then yeah, let's see how much voltage we actually have here. Yeah, we are on the 1000 volt range, and yeah, that's 230 volts or so. So I can go to a lower range here to 250, and then we are on the 250 scale, of course, because that's more accurate, and that's bang on 200. So 200 volts. That means times 4, yeah, 2, 4, 6, 8, 800 volts. So zero equals 800 volts. That's good to know. And yeah, now I want to connect a test resistor here between ground and the output. And for this I have these ladder of resistors here. It's a 2.145 megohm resistor. Of course, I just want to use one of them. Okay, just let me connect it quick. So plus to, oh, come on. Bite your alligator clip. So make good contact there. That's important. Okay, that's one side. Then the other side of the resistor goes to ground, of course. Okay. So then, yeah, let's test that. Okay, now under load we have less voltage. That's 140. Yeah. Okay. Also under load, it's 4 times 140, and that's 600 volts. So okay, it's also good to know. And let's see if it's repeatable. Yeah, it's spot on where it was before, so that's good. And now I want to measure the voltage across this combined series resistor here. So I have to reconnect. So yeah, basically I want to really measure across all these resistors here, no matter what. So I clamp it here. So it's connected on that side here, and now I have to connect it here. But no, let's make it just the other way. Then goes to here. So yeah, basically the multimeter is now connected across these series of resistors here. And yeah, I go back to the 1000 volt range. because now the voltage can go higher depending on the load resistor. So yeah, you see the needle moves. Okay, and that's yeah, 200 volts. So I go to the lower range, and now we're on the 250 scale, and that's basically 160, 70, 80, 180 volts. So $180. Okay, let's repeat that. Yeah, actually, yeah, two divisions here mean that it's yeah, 10 volts. So it's not 180, it's 190 volts. So, and now, yeah, if I just don't know the resistor, because in the usual test case or use case, I don't know the actual resistance here. So let's try if I can just calculate it. And that's our ISO. And yeah, the basic formula for calculating the resistor is U divided by I, so that's the voltage divided by the current. And yeah, basically I need to know the voltage across this isolation test resistor here, and that's easy to calculate because yeah, it's the total voltage under load, that's 600 volts, minus the voltage across that series resistor here, and that's 190 volts. And then I need the current, and the current in a series of resistors is the same. It's independent if it's measured here or if it's measured there at that test resistor. So I know the value of this resistor here, and I basically can calculate then the current, because yeah, it's basically the voltage across this resistor here, and that's the 190 volts, divided by the resistance itself, which is 806k ohms. And yeah, then let's see what the calculation gives us. Yeah, that's 1.74 meg. 1.74 mega ohms. And yeah, I mean 1.74 mega ohms compared to 2.145 mega ohms, which it is really, that's really a difference here. So I have to find out why there's this mismeasurement. Something seems to be wrong here. Yeah, and I also want to measure the voltage across that series resistor. And for this I connect it to here with the plus and to here with the minus, because then I measure totally across these four resistors here. Let's see. That's 201. 201 volts, and Yeah, let's also measure the total voltage. And for this, I connect ground to ground and plus to here, because then I measure the voltage across just one resistor of these 4 resistors. So I measure 25% of the total voltage. I just have to, consider that. Let's see what we have. And it's 166 volts. And 166 times 4 is okie dokie. So now I have both voltages I need to calculate the value. And it's, 1.86 meg ohm. And 1.86 is pretty, or is, closer to 2.145. I mean, it's just, 87% or so. So that's an error of 13%. So I mean 13% error is a bit high, but when I consider this coarse preliminary test setup, I mean all the cables here, they are not rated for 800 or 600 volts, and even the resistor here, I mean it's on the limit, the voltage limit. Maybe it changes its resistance. I'm not sure. But that doesn't really matter, because that's good enough, not for measurement, but for testing. Because the idea for this setup here is to test an installation circuit for isolation resistance, because there was an issue with error currents to ground, and that's sufficient to do that, because I mean a good value in home appliance system is for example 5 mega ohms, and with this setup here I can easily see if it is really 5 mega ohms or if it's just 500 kilo ohms, which would be way off, and that's what I want to test, if it is really good or if it is off. I don't need an accurate measurement of that resistor here, so that's fine. That on a real case, because these brackets here were outside for about 2 years, and it's made out of plastic, and the plastic itself is a good isolator, but you may see on camera here that there is dirt, and here is even more dirt. So I think that would give a lower resistance than the plastic material itself. So let's connect that. So I connect one side here and the other side here. Just let's see what it does. Okay, now we have a voltage, 25% voltage of 224. So 224 times 4, which gives us total voltage of 896 volts. Because, yeah, you see the voltage is not stable because it heavily depends on the load. And the load is now much, or the load resistor is now much higher, I assume. And yeah, that obviously leads to higher generator voltage because, yeah, it's not loaded so heavy. And then that's again measure the voltage across that resistor here. That's here, the voltage. Let's see. Oh, okay. It's pretty low. It's just 108 millivolts. Really? I can't believe it. Let's try it again. No? 100? Yeah, let's say it's... Yeah, and if I put that into this formula, let's do it again. That gives us our ISO of 7.22 gigaohms. Okay, so obviously it's not so bad. Just to confirm it, I wanna use the multimeter to test it. Let's see. So I've put it in the ohm range. Let's see if he can measure something. And you see, no, it's not possible to measure it because, I don't know, I think 10 meg or so is the maximum resistor he can measure, or it can measure. So you see, the high voltage testing can measure much higher resistance. So that's nice. It's just, yeah, the dirt does not cause an isolation issue, but maybe, the mechanism behind it in nature is that humidity builds up inside that dirt, and the dirt keeps the moisture there for a longer time. And yeah, the dirt combined with humidity, that's what's giving a lower resistance. So I may try to make it wet just a bit. Just let me try that. Okay, so I've put some water on it, or sprayed it with water. So let's see in which resistance range we are now. Just have to be careful because my hands are wet now. I really have to get my hands off there because I don't want to be zapped. So let's see. This voltage across this resistor here, series resistor, should be higher because a higher current should flow because I expect a lower resistance there. Let's see. That's 308. 308 volts. And when I measure the voltage across this resistor, so I measure 25% again of the total voltage. It's 145, and 145 times 4 is 580. 580 volts. So let's see what kind of resistance this gives. Now our ISO has dropped dramatically. So you see, instead of over 7 giga-ohms, we have just 712 kilo-ohms. And yeah, that's the difference I meant, because yeah, that is the difference between a good isolation, a pretty good isolation, and a bad isolation, because that's way less than 5,000 kilo-ohms. So if the isolation value is below or equal 7.7 kilo-ohms, only then it triggers. The RCD triggers there. So we are way above this value here. So the RCD would not trigger, but the isolation resistance is still bad. And yeah, I don't want to have a system in my home supply system with an isolation voltage of such a low value, because that's a risk. Because if I calculate how much current would flow through to Earth or to the person that connects to the badly isolated appliance, and that's a value of 323 microamps. So yeah, I mean, it probably wouldn't kill you, but it's definitely not the current you want to experience. So yeah, I call this a full success. It's not an absolute accurate measurement device, of course, but it's capable of testing if a system is good isolated or bad isolated. So yeah, I would kind of end this video here. Thanks for watching. See my video description for the product links. You can support my channel by clicking on these when you're buying things. And I will see you next time. Bye bye.